All right, so early on in my research, I wanted to examine this question of when did we know what we know today as it pertains to the periodic table of elements and the human chromosome count. And the short answer to this question is the year 1956. This is when it was published that humans had 23 pairs of chromosomes. And during that same time, as it relates to the periodic table of elements, you have at that point scientists already having begun synthesizing new elements. And I believe in 1955, mendelevium, and that's element 101, had just been synthesized. And since the 1940s, they've been pretty successful synthesizing heavier and heavier elements at that point, with no real indication of slowing down or finding any sort of limit. So you have that, and then you have these periodic tables being widely distributed. With them, it's really easy to extrapolate that the seventh period would perhaps eventually end with the element 118. So you've got that delineation of naturally occurring elements and synthesized elements, and that second delineation at the very end of that, at 118. So as it relates to this numeric relationship, you've got these nice delineations, and you can match it up pretty well at that point. Really, the only piece of the puzzle that's missing is that plutonium had not yet been discovered to be a naturally occurring element. And that's just like the last little tiny tidbit, I'd say. But apart from that, there's certainly sufficient information out there that you could correlate this numeric relationship between prime and composite numbers and associate that with the periodic table of elements, find something striking with this relationship between those two things, and then also find that striking relationship as well with the human chromosome count at that same time. So 1956. Now, the reason why I wanted to answer this question was, because really I wanted to answer this question, am I the first person to discover this? And I find that doubtful, because 1956, that's 63 years ago. And there's, 7.5 billion people alive today. Back in the mid-50s, it was 2.5 billion. So that's a lot of people over a large span of time, or large enough span of time, with this information being available. Now, how readily available that's over that span of time is variable. Not necessarily every person has easy access to the periodic table of elements or understanding the human chromosome count at that point. But at least they were published someplace, and its visibility over that span of time was increasing. And now easily today with the internet, it's just, anyone can look this stuff up. So, but it's still billions of people having plenty of time to stumble upon this before me. And it is possible I might be the first, but again, I'm generally against that idea. But, so yeah, there's that. Now here's the thing, I did find some very interesting information as well relating to these questions. One of it is the second delineation, at the end of that period of debate as it relates to this numeric relationship, 117. And so it's this idea of when was element 118 first seriously considered. And I stumbled upon this. I'm referencing Wikipedia right now. This is the Wikipedia page on oganesson, element 118. And this little excerpt here So in terms of its history of discovery and early speculation, the Danish physicist Niels Bohr was the first to seriously consider the possibility of an element with an atomic number as high as 118, noting in 1922 that such an element would take its place in the periodic table below radon as the seventh noble gas. Now, if you actually clicked that link, it actually takes you to this very, very nice table. I absolutely love this table, especially as it relates to this numeric relationship. Now, this is his 1922 table. It appears to be published in the journal called The Theory of Spectra and Atomic Constitution. And this was published by the Cambridge University Press. And again, just absolutely amazing table here, very clear. You've got the symbols of the elements, and then you've got their atomic numbers, just very clearly spaced out. And if you compare this to other tables at the time, there's very few where you could actually extrapolate that the seventh period would end at 118. But this one, it makes it very clear. It's very simple, and it's got it there for you. And what's really nice about it is, as it relates to the numeric relationship, that large period where primes would dominate is largely filled in by all these known elements back in 1922. And at that time, they hadn't begun synthesizing elements beyond uranium yet. So in that area between uranium and 118, it's actually just entirely blank. So, looking at this numeric relationship, provided you had known it, you would see a very striking correlation there. Really, the only thing missing from this chart is elements 93, 94, neptunium and plutonium. But they wouldn't even be synthesized until the 1940s, and in the following decades, discovered in nature. So, but I mean, apart from that, this is like a grand slam practically. Absolutely love this chart. So yeah, so there's that. So 1922, right? So now this next little tidbit, we are looking at the Wikipedia page for the periodic table. And so we're examining the history of it, and we are now at 1923. So this little excerpt here says, the popular periodic table layout, also known as the common or standard form, is attributable to Horace Groves Deming. In 1923, Deming, an American chemist, published a short Mendeleev style of his chart, and then a medium 18-column form of the periodic table as well. And Merrick and Company prepared a handout form of Deming's 18-column form in 1928, which was widely circulated in American schools. And by the 1930s, Deming's table was appearing in handbooks and encyclopedias of chemistry. It was also distributed for many years by the Sargent Welsh Scientific Company. So now we've got Niels Bohr's chart in 1922, right? It's published in this academic journal out of Cambridge. But now we also have Deming's chart from 1923, and this is the one that gets widely distributed. And if we actually go to look at this table, I mean, it is in a form very similar to what we're used to seeing today. That part's at least true. We do have the lanthanide series expressed as rare earths, so that's elements 57 through 72 on this chart. So you can see that it's truncated in the lower left, and in the lower right it's spelled out further. However, you don't actually have the actinide series truncated the same way. You just have actinium, thorium, PA, is that palladium, I think? No, that's not palladium, but I forget which one element 91 is. Oh well. And then, of course, you have uranium. Now, if you weren't thinking too much about it, you're counting up from uranium if you wanted to extrapolate that to the end of the 7th period. In the form that it is, it doesn't take you to 118. It's like 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4 potentially. So this would only really take you up to 104 if you're trying to extrapolate this out in its current form. And then you'd have to occur to you that perhaps that 7th period would also have that truncated actinide series. So, but that isn't going to be developed for about a decade after this. So yeah, and then so this is the 1923 chart, and then he also comes out with a 1925 chart as well, and this thing even looks even more complex. I mean, yes, it's still generally there, but I mean, there's so much more other information. It's like you can't really make heads and tails of it. This is not the kind of chart for the layman to really look at and examine. So, but this is what ended up being widely distributed, and it's very hard to correlate this with this numerical relationship by comparison. So yeah, so you've got this in 1922, you've got this really nice chart that correlates very strongly that has a limited publication. And then you have this broad publication the next year that that ultimately in the succeeding years after that, it's widely distributed, but it's not readily apparent that it'd make any connection to this numerical relationship. So whether that's on purpose or by accident or by design, it is kind of hard to say, take it in isolation. So let's see here. We are still on the periodic table Wikipedia page. And then we've got this little nice excerpt here. In 1945, Glenn Seaborg, an American scientist, made the suggestion that the actinide elements, like the lanthanides, were filling an F sublevel. Before this time, the actinides were thought to be forming a 4th D block row, and Seaborg's colleagues advised him not to publish such a radical suggestion, as it would most likely ruin his career. Now, as Seaborg considered he did not have a career to bring into disrepute, he published it anyway. And Seaborg's suggestion was found to be correct, and he subsequently went on to win the 1951 Nobel Prize in Chemistry for his work in synthesizing the actinide elements. And if we actually look at Seaborg's version of the periodic table, yes, you do see that resolution with the actinide series. And once we get to this chart here, this is 1945, and yes, you could actually extrapolate these elements heavier than uranium here to the end of the actinide series, and if you put that in its place where it's truncated in the lower left-hand side of this chart, and you have to get rid of those other this superfluous information there following it. But you could extrapolate from that to the end of the 7th period and get element 118 that way. And so this is and that's when we have the periodic table in its form as we understand today. So yeah, that's that. So it's really not until 1945 where it's widely distributed that you could look at the periodic table, understand these naturally occurring elements, and see the beginnings of the synthesized elements, and then also make this extrapolation to the end of that other period to 118, and see how that would correlate with this numerical relationship and its points of delineation as well. So yeah, 1945. So now here's the thing. That's the periodic table of elements, right? But then we also have the human chromosome count. Now, I said previously that it was asserted in 1956. It was discovered in 1956 that human beings had 23 pairs of chromosomes. However, before that, it was thought to be 24. And what's very interesting is that it's around about this very same time period as the 1920s, where you've got Niels Bohr's chart and then and Deming's charts there. So here, let's actually examine the chromosome count real quick. All right, so this is from the Chromosome Wikipedia page, and this is an excerpt under this historical note here. So investigation into the human karyotype took many years to settle the most basic question: how many chromosomes does a normal diploid human cell have? In 1912, Hans von Winnewater reported 47 chromosomes in spermatogonia and 48 in oogonia. So I think that's male sex cells and female sex cells. He concluded an XXXO sex determination mechanism. That is to say that females will have one additional chromosome and then males won't have that additional chromosome. Now, Theophilus Painter, in 1922 was not certain whether the diploid number of man was 46 or 48. At first favoring 46, in 1922, mind you, he revised his opinion later from 46 to 48. And he correctly insisted on humans having an XXXY system. That is to say that we have the same number of chromosomes, but males have a slightly different chromosome. It's like a smaller version of what women have. But here, let's look at this again. 1922, he's not certain whether the number is 46 or 48. At first favoring 46, and he revised his opinion later from 46 to 48. He got it wrong. He thought he was right, second-guessed himself, and got the incorrect conclusion, right? That's 1922, the same year that Niels Bohr published that very, very clear chart. So now we go on. So that's what he thought in 1922, but those findings weren't published until the following year in 1923. And so we can look at this. This little excerpt is actually from a Wikipedia page titled Arguments from Authority, and it's kind of like a logical fallacy, right? So an authority makes some sort of assertion, and because that person's the authority, they must be the ones that are correct or whatever, right? And so if you're trying to make a discovery or use some basis of scientific information with an argument, you're using it upon the basis of someone else's work based on that they're an authority, regardless of whether or not they might be right or wrong. So if we look at this logical fallacy here, we've got a little excerpt, very interesting excerpt on this page. Scientific knowledge is best established by evidence and experiment rather than argued through authority. As authority has no place in science, Carl Sagan wrote of arguments from authority, one of the great commandments of science is mistrust arguments from authority. Too many such arguments have proved too painfully wrong, and authorities must prove their contentions like everybody else. An example of this, the use of appeal to authority in science can be seen in 1923, when leading American zoologist Theophilus Painter declared, based on poor data and conflicting observations he had made, that humans had 24 pairs of chromosomes. From the 1920s until 1956, this continued to be held based on Painter's authority, despite subsequent counts totaling the correct number of 23. Even textbooks with photos showing 23 pairs incorrectly declared the number to be 24, based on the authority of the then consensus of 24 pairs. This seemingly established number created confirmation bias among researchers, and most cytologists expecting to detect Painter's number virtually always did so. Painter's influence was so great that many scientists preferred to believe his count over the actual evidence. And scientists who obtained the accurate number modified or discarded their data to agree with Painter's count. So let's kind of sit and think about this for a little bit. All right? 1922, Painter is thinking that it's 23. He's thinking that it's correct, right? Or that's the assertion that's what he's thinking. And then he changes it to be this incorrect count, which holds for 23 to 56 that's 33 years. So here's the thing. So this numeric relationship ties the human chromosome count to the periodic table of elements. But between those two fields, you also have this temporal correlation round about the 1922-1923 time frame, right? You've got this very striking, clear chart you can very easily correlate the elements to this numeric relationship, 1922, right? But then you've got what's widely published being very convoluted that following year, right? And at that same time, you've got this little hiccup relating to the human chromosome count. Again, 1922, he's thinking it's 23 pairs, and publishes that following year in 1923 the incorrect count, which holds for another 33 years. So might there be something to that, right? Very, very interesting, I think. Now, if you had seen Ben Stein's documentary, Expelled, No Intelligence Allowed, right? It actually, later on in the film, it actually goes into a little bit of, it actually gets into, the rise of Hitler and, the Nazis in the 1940s, right? See, here's the thing, I believe Hitler's March on Munich, I think that was in 1923 also, right? So you've got academia, which I'm not to say that I've got a surefire evidence of, although there are indications that it might be possible that there was some sort of coordinated effort to suppress this very clear and accurate information in the early 20s. And then along that same time, you've got the rise of Hitler in Germany, his March on Munich. He gets tried and convicted of treason, and he's sentenced to 5 years in prison, which gets shortened down to a year or a couple of months or something like that. He dictates Mein Kampf, and you have this huge rolling ball around that same time. It's with these temporal connections, and with Hitler's final solution pertaining to the Jewish problem, right? A lot of it's predicated on eugenics, right? Which is very much sort of like this evolutionist outlook, right? As indicated in Ben Stein's film. So, I'm not to say I'm trying to condemn academia outright. It's certainly in 1923, anyone alive at that time wouldn't predict what Hitler would do, right? But it's just kind of something curious to think about. Were there forces controlling academia to curtail this information as to not stand in Hitler's way and just kind of let those world events play out to some sort of grander design, So it's really kind of curious to think about. So yeah. Just something really striking there that I found. You know, that not only is there this numeric relationship tying these two fields, but as it relates to kind of discovering this numeric relationship tying these two fields, it's just and being so temporally interlinked, you know, within a year. It's, yeah. So yeah, I think I'll leave this video at that for now. And so yeah, I'm Brian Downing, and I will see you next time.